Hi, and welcome to the video presentation of Group 8's Soccer Playing Robot, completed as part of the EGB320 Mechatronics Design 2 course at QUT. This project was inspired by the RoboCup Small Size League, or the F180 League as it's otherwise known. RoboCup initially made its first appearance in 1997. Since then, it has encouraged research into robotics, such by the year 2050, robotic soccer players will beat other human players. The F180 League has since seen dozens of robotic soccer teams annually compete against each other. Group 8 was tasked with designing a fully autonomous soccer-playing robot based on the modified specifications from the F180 League. Due to our team only having 3 members, our robot was required to push the ball into a goal while avoiding static obstacles which represented other players. A local vision system, a conventional 2-wheel drive system, and an AI navigation system were utilized to achieve the final product. Let's further explore each subsystem.
Hello, in this part of the video, we'll be looking at the robot chassis and powertrain. Firstly, looking at the overall design of the chassis, which is made up of 7 3D printed parts. An advantage of having 3D parts is that it allowed our team to easily make small weekly changes and focus on an overall neat and compact design. The robot's powertrain contains 3 major subsystems: the battery, the control, and the motors. The supplied lithium-ion battery contained 2 18650 cells, which could supply between 4.2 and 3 volts per cell without damage. Having 8.4 volts to regulate, the control system utilizes a half bridge, which is specifically designed for controlling motors, allowing forward and rear rotation and varying degrees of power. Moving over to the motors. The motors are worm-driven, with customizable gearbox ratios. These motors are currently set up to produce 47 RPM with the 85mm wheels attached, which was able to meet the speed requirements, both high and low. Lastly, the integration between the Raspberry Pi and the half bridge requires 1 PWM and 2 logic pins per motor. By alternating the logic pins high-low or low-high, the wheels rotate in each direction. By using an extra PWM signal to the H-bridge, the power delivered can be altered and the robot's speed. Thank you for listening.
Hi, I'm Chris, and I was responsible for the vision system for our robot. The vision system is the robot's primary source of sensory input, which provided the AI navigation system with all its necessary information about its surroundings, which in turn assisted the robot to move to an area, to acquire a ball, and then score a goal. This was achieved by color filtering. In this situation, the hue saturation value, or HSV, color space was chosen because the base color is being encoded separately from the ambient light. Thereby finding the hue and saturation ranges of the object, we can then start to define a filter to process each captured frame from the camera feed. By choosing an upper and lower threshold value, we can identify our object in the image and mask everything else. Our output image should only contain our object. Then the central point of each object could be found. Then the range and bearing can be calculated using 2 formulas. This information was then passed onto the AI navigation system.
Hi, my name is Nisarg, and I was in charge of the navigation and AI subsystem for the soccer robot. To enable the robot with basic soccer playing functionality, a state machine was created with many iterations throughout the testing process. The robot would start in a search for ball state and then progress through the state machine depending on the sensory inputs. This system was able to control the translational and angular velocity of the robot using the drive system. This, in combination with the reactive navigation system, allowed the robot to consistently move towards the ball and identify all the different components present on the playing field. Based on this list of components, the robot aimed to avoid any obstacles that it would encounter and move toward the desired goal when required to do so. However, this level of functionality was not incorporated at the time of the final demo due to lacking progress with the vision system. At the time of the demonstration, the vision system was unable to provide meaningful range and bearing information regarding the obstacles and goals. Therefore, for the final presentation, Group 8's soccer robot was not able to score goals, but did manage to consistently obtain the ball and avoid obstacles with some consistency.